Welcome to the High Voltage AI Podcast. It's Friday, July 4th, and before we dive into today's deep dive, we really want to take a moment just to offer our deepest thanks to all service men and women actively serving, retired, and veterans for your incredible service to our country.
Absolutely. Truly your dedication, it really lays the foundation for everything we discuss and, well, everything we build. It's an honor to acknowledge that.
It really is. So today's deep dive, it's the grand finale, you could say, of the PXRD newsletter's week-long series. It's all been crafted specifically for electric utility engineers.
Right.
It's been quite the journey this week, hasn't it?
It absolutely has. Yeah, we kicked off Monday really grappling with that data center tsunami that's hitting, 75% of utilities?
Right.
Then Tuesday, we unpacked that staggering shift, from 4% to 15% grid consumption in just 6 years.
Incredible numbers.
Yeah. Wednesday brought us face-to-face with the distribution design side of things when 50 megawatts becomes, the new normal. And then yesterday, Thursday, we dug into the transmission planning bottlenecks and those queue crises everyone's talking about.
So after all that groundwork today, we're really zeroing in on something critical. The practical engineering solutions. The ones that actually work.
Exactly. What's effective on the ground.
Our mission for this deep dive, then, is to pull out the most important nuggets of knowledge. What's truly making a difference, and, let's be honest, what isn't, when utilities try to fast-track these massive data center connections.
Yeah, what are the real lessons learned?
Think of it as your shortcut, really, to getting well-informed on this critical topic. It's moving so fast. So where should we begin?
Well, it's pretty fascinating how some utilities have just managed to completely rewrite the playbook. Let's start with Xcel Energy. Their infrastructure banking model is quite something.
Infrastructure banking. Okay, that sounds almost more financial than engineering. What was the specific challenge they faced? What pushed them towards this?
Right, so they had this huge 200-megawatt data center request land on their desk.
Okay.
And the energization deadline was just 18 months.
18 months for 200 megawatts. Wow.
Yeah, and the problem, standard transmission upgrades usually take 5 to 7 years.
Easily.
Plus, they just didn't have the existing substation capacity. It was, a classic square peg, round hole situation, but with an impossible timeline attached.
So how did they bridge that huge gap? What was the shift in their thinking?
They completely reimagined it. Instead of waiting for that confirmed load, they combined pre-positioned infrastructure, modular substation design, and some really innovative financing.
Okay, break that down. Pre-positioned infrastructure.
They started with some really detailed market analysis, identifying 3 high-probability development corridors.
Right.
Then, and this is the crucial bit, they made speculative investments. They actually built 230 kilovolt line capacity upgrades using advanced conductors before any confirmed load. It was a calculated gamble.
Building before the customer commits, that's a big financial risk. How did they manage that? And what were the technical details that made it work?
The modular design was absolutely key. They built these 230/69 kilovolt substations, but with spare positions already included.
Planning for growth.
Exactly. Designed for a 200-megawatt ultimate capacity, but built in 50-megawatt chunks. This let them scale up efficiently as the demand actually showed up.
Okay.
They also went hard on fast-track processes, parallel permitting and construction, standardized protection packages, pretty sophisticated scenario-based load forecasting, too.
The results sound impressive. You said they slashed the timeline.
Hugely, from that typical 5 to 7 years down to an average of just 12 to 18 months.
Incredible.
Plus, they got about a 30% reduction in the per megawatt infrastructure costs just through economies of scale. And they met 100% of their requested timeline commitments.
And what really stands out to me is that figure only 25% of that pre-positioned capacity is still unused after 3 years. That shows some really good forecasting.
It really does. And the big takeaway from Xcel's infrastructure banking, it's that data center developers, they're surprisingly predictable.
Interesting.
Their site selection isn't random, so that proactive market analysis, it's not just smart, it's like having a predictive superpower.
Right.
Modularity clearly pays off, letting those expandable designs handle uncertain timing and sizing. Crucially, though, you absolutely need regulatory buy-in for that kind of speculative investment.
Can't do it without them.
No. And finally, they learn to avoid overbuilding. You don't want stranded assets.
Makes sense.
Okay,
next up, let's shift focus to Duke Energy and their integrated planning approach. What was the pressure point there? What made them rethink things?
For Duke, it was just the sheer volume of data center development in North Carolina. It created these intense, localized transmission constraints and real distribution system stress, especially around Charlotte and Raleigh.
Right, the big metro areas.
Yeah. Duke quickly figured out their traditional way, transmission studies first, then distribution studies. It was just creating unacceptable delays. It wasn't efficient.
So they basically said, hold on, this sequential thing isn't working, and decided to break down those internal walls.
Exactly that. They ditched the traditional approach and moved to a truly integrated method. They started doing joint, simultaneous transmission and distribution impact analyses.
Okay, simultaneous studies. What else?
A core innovation was their data center substation standard. They developed these multi-voltage substations, think 230/69/25 kilovolt, optimized specifically for data center loads.
Tailor-made, pretty much.
Designed for that high 95% load factor with very little diversity, N-1 contingency at all voltage levels, enhanced voltage regulation, harmonic filtering built in, and a 50% future capacity margin.
Wow, that's incredibly thorough. Really future-proofing it. How did this integrated thinking actually speed things up?
The impact was huge. They managed to cut study time from, say, 18 months down to maybe 6 to 9 months.
Half the time or less.
Yeah. And construction timelines sped up dramatically.
Yeah.
Projects that usually took 36 months were getting done in 24.
A full year faster.
Right. Cost predictability got way better, too, shifting from that traditional plus or minus 25% range down to plus or minus 10%.
Much tighter.
And get this, a 40% reduction in engineering hours per project. It's just a powerful example of how coordinating across disciplines unlocks massive efficiencies.
Absolutely. Okay, our third success story takes us to a very different place. Xcel Energy's desert data center model out in Las Vegas. What were the unique constraints they were dealing with?
Well, the Las Vegas desert, it presents some pretty unique challenges, right? Limited water resources, obviously.
Huge issue there.
Yeah. And the need for massive transmission capacity to serve these very concentrated high-density loads. This wasn't just connecting one facility. It was about enabling a whole new economic engine out there.
And Xcel Energy's response was this data center campus idea. How does treating multiple facilities as one integrated piece of infrastructure solve those desert-specific problems?
They essentially master-planned the electrical infrastructure for a huge 500-plus megawatt development.
Wow.
This meant shared resources like a 500 kilovolt direct transmission interconnection for the whole campus, common substations, even centralized backup generation.
Sharing the big-ticket items.
Exactly. And crucially for the desert environment, they put a heavy emphasis on water-free cooling, designing for air-cooled data centers, completely eliminating the need for cooling tower water.
That's critical out there. And they took it even further, integrating renewables right into the campus, didn't they?
They did. They co-located a 200-megawatt solar farm with shared interconnection. And a big battery, too, a 100-megawatt/400-megawatt-hour system.
So built-in generation and storage.
Precisely. This gives them microgrid capability and lets the campus provide grid services. It becomes a dynamic participant, not just a passive load. Their designs were also specifically beached up for extreme temperatures and dust, obviously, and they use smart controls for load management and those active grid services.
The results seem pretty compelling. 18 months on average from request to getting the power on. A 60% cut in water usage compared to traditional data centers.
That's massive.
And the campus actually provides frequency regulation and voltage support back to the main grid. Plus, it enabled, what, $2 billion in private investment?
Yeah. It really shows how utilities can be major enablers for economic growth, even when the environment is challenging.
These three cases really highlight that innovation, proactive planning, and just being willing to adapt to the old utility model are absolutely essential.
Couldn't agree more. It's about flexibility and foresight.
Okay, now let's pivot. We celebrated what works, but it's just as important, maybe even more so, to learn from the expensive mistakes. What were some approaches that, looked good on paper but just failed spectacularly in practice?
Oh, there have been a few. One major misstep we've seen pop up more than once is what you could call the parallel feeder solution.
Parallel feeders. That sounds like trying to use existing distribution infrastructure.
Yeah.
Right. What was the idea and why did it seem like a good plan at first?
Exactly. The concept was, okay, we have this big data center load. Let's just serve it with multiple parallel 12.47 kilovolt feeders. instead of upgrading to a higher voltage.
Okay.
And it seemed logical, right? You use existing equipment types, the initial infrastructure cost at that voltage seems lower, and your protection and operations folks are familiar with it. It feels like an incremental step.
So where did it fall apart? What was the fatal flaw?
Voltage regulation. It's basically impossible to maintain that strict plus or minus 2% voltage regulation data centers need when you're juggling multiple parallel feeders.
Ah,
That quickly leads to incredibly complex protection coordination headaches, maybe even impossible to solve cleanly. And ironically, even though it looked cheaper up front, building and maintaining all those parallel feeders often ended up costing more than just doing a single higher voltage solution right the first time.
right.
It's a classic case of trying to fix a transmission scale problem with distribution scale tools. It just doesn't scale up properly.
That's a really critical lesson, especially for distribution engineers. What was the next common approach that backfired?
Applying the standard industrial rate structure directly to data center customers with no changes.
Okay, I could see why that would look appealing. Simple, right?
Nah.
No new rate design needed, works with existing billing systems, probably less hassle with regulators initially.
Exactly. It looked like the path of least resistance.
But it clearly didn't work. Why not? What broke?
The fundamental problem is the load factor mismatch. Data centers run flat out, maybe 95% load factor consistently.
Right, unlike traditional industry.
Totally different profile. And traditional industrial rates just aren't designed for that. Their assumptions got completely blown up. The consistent high load got hammered by demand charges, especially those ratchet provisions.
Ouch. Penalized for being consistent.
Pretty much. This led to really unstable revenue for the utilities, and maybe the biggest issue, it resulted in cross-subsidization. Other customers ended up effectively subsidizing the data center infrastructure because the rate structure just didn't fit the load profile.
So, lesson learned. Data centers really need their own purpose-built rate structures. That's a big one for utility management and regulators.
Absolutely critical.
And the third failed approach, the wait-and-see planning strategy. I think I could guess why this seemed prudent financially.
Oh, yeah. It's the traditional conservative utility mindset, right? Avoid stranded investment at all costs. Wait until you have a signed contract, a confirmed commitment, before you start planning the major infrastructure.
Seems like sound financial management on the surface.
It does. It aligns with how things were often done.
But in a market moving this fast, wait and see basically means watch the business go down the road. What were the real consequences?
You nailed it. It created this massive timeline mismatch. Infrastructure, especially transmission, just takes way longer to build than these customers can afford to wait.
They'll go elsewhere.
Exactly. Utilities using this approach suffered a huge competitive disadvantage. They lost lucrative customers to competitors who had infrastructure ready or nearly ready. It also often led to much higher costs in the long run. Those emergency fast-tracked upgrades, they can cost 200, even 300% more than properly planned construction.
Wow.
And of course, the region misses out on significant economic development opportunities. The lesson is really stark. In these high-growth data center markets, reactive planning is pretty much a guarantee you'll lose customers.
Okay, so we put together the successes and these expensive failures. What does a practical, actionable game plan look like for utilities? How do you implement something that works?
We sort of synthesized it into a 4-phase approach that seems to capture the best practices. Phase 1 is all about market intelligence.
Yeah.
Think months 1 to 6.
Okay.
This means really granular site analysis, getting out there early, talking to developers, doing sophisticated scenario-based load forecasting, not just trend lines, and a really thorough assessment of your existing system capacity. It's about deeply understanding the potential demand before it fully materializes.
So know your market inside and out first. Then what?
Then you move into action. Phase 2 is strategic infrastructure investment. This might be months 6 to 18.
Right.
This is where you focus on upgrading those transmission constraints along the high probability development paths you identified, building those expandable modular substations, developing standard templated solutions so you're not reinventing the wheel every time, and crucially, getting that regulatory approval for the infrastructure banking approach, if that's your strategy.
Laying the groundwork proactively.
Exactly. Then you're ready when the customer calls. That brings us to Phase 3, the fast-track customer process. This kicks in around month 18, maybe earlier, and it's ongoing.
This is the execution phase.
Right. Implementing rapid, say, 3 to 6 month study processes using those pre-engineered solutions you developed. Actually executing the parallel transmission and distribution construction. using standardized interconnection agreements to speed things up. And really important, deploying dedicated, specialized teams who know the stuff inside out.
Makes sense. And it doesn't stop there, right?
Yeah.
It's not just build it and forget it.
No, definitely not. Phase 4 is operational excellence, and that's continuous. It means ongoing improvement through really detailed performance monitoring, staying proactively engaged with the data center industry because their technology changes fast too, and integrating new grid technologies as they mature and become viable.
It's a cycle of learning and adapting. Okay, beyond that framework, what about specific technical best practices? What really works on the ground? Let's start with substation design. What defines success there?
Multi-voltage capability is huge. Being able to handle, say, 230, 69, and 25 kilovolts in a single station gives you immense flexibility.
Right.
Modular expansion is key, too. Designing for 50 to 100% future capacity right from the start. Build the space, build the pads, even if you don't install all the transformers initially.
Scalability.
Yes. And reliability features are non-negotiable. N-1 contingency at all your voltage levels. Plus, built-in power quality features, you need precise voltage regulation, plus or minus 2% or better, and harmonic filtering. These loads demand it.
Got it. And on the protection system side, what approaches are proving most effective for these critical loads?
Standardization is king here. Pre-engineered, standardized protection schemes let you deploy much faster. Communication-assisted schemes using fiber optics for high-speed coordination between relays are vital.
Speed and coordination.
Absolutely. Redundant systems for critical applications you can't afford a single point of failure. And robust remote monitoring through SCADA systems is essential for visibility and quick response. These systems need to be smart, fast, and really resilient.
Makes sense. And what about construction? How are the leading utilities actually getting these projects built faster and more efficiently?
Having dedicated, specialized crews just for data center projects makes a huge difference. They get really good, really fast.
Expertise matters.
It really does. Also, aggressive long-lead procurement. Getting those big transformers and breakers ordered way in advance is critical to hitting timelines.
Avoiding supply chain bottlenecks.
Right. Using modular construction techniques with prefabricated components whenever possible, that speeds up on-site work dramatically. And really pushing for parallel design and construction activities, overlapping timelines wherever you safely can.
It sounds incredibly robust from an engineering standpoint, but it also sounds expensive. What financial models are making this work? How do you make it palatable for everyone involved?
Yeah. The financial side is crucial. On the customer cost-sharing front, we're seeing success with hybrid funding models. Maybe the customer pays 50 to 70% of the dedicated infrastructure, costs the stuff only they benefit from.
Okay. A shared investment.
Right. Utilities are also using performance incentives linked to reliability, offering specific economic development rates to attract these businesses, and sometimes even premium rates for customers who need, exceptional reliability or power quality guarantees.
And how does the utility recover its share of the investment, especially for that proactive, pre-built infrastructure?
Getting regulatory approval for that infrastructure banking concept is absolutely paramount. You need to make the case effectively.
Right.
Ensuring that those reasonable, prudent infrastructure investments can be included in the rate base is key. Using economic development riders can help offset some costs across the board. And carefully allocating costs based on who benefits. Sometimes these upgrades benefit multiple customers or improve overall system reliability that helps justify the utility's share of the investment.
So it's a mix of customer contribution and smart rate design and regulatory engagement.
Exactly. It needs a multifaceted financial approach.
Okay, so after looking at all these projects, the successes, the failures, the strategies, what's the bottom line? If you had to distill it down, what are the common threads, the characteristics shared by the utilities who are getting this right?
It really boils down to, I think, 6 key things we see consistently. First, proactive infrastructure. Utilities that pre-position capacity, that build ahead of the curve, they just consistently outperform reactive approaches, both on timeline and customer satisfaction. Being ready matters.
Okay, proactive infrastructure, number 1. What's second?
Standardized solutions. Using those template designs, those standard processes, it dramatically cuts study time, like we saw, from 18 months down towards 6 months, but without cutting corners on the engineering.
Efficiency through standardization. Got it. Third.
Integrated planning. That joint transmission and distribution planning, it knocks down those internal silos, eliminates interface problems, and really does shorten the overall project timeline significantly.
Makes perfect sense. Fourth characteristic.
Financial innovation. Those new cost allocation models we just talked about. Finding ways to appropriately share the investment between the specific customer and the broader ratepayer base is absolutely critical to making these large projects economically viable.
Right, the money has to work.
Yeah. Specialized resources. Having dedicated engineering and construction teams, they just build up expertise and efficiency that you can't get with general rotating crews. It's about developing that deep institutional knowledge for these specific types of projects.
Focus breeds expertise. Okay, and the sixth and final characteristic.
Market engagement. Getting out there early and talking continuously with the data center developers. It leads to much better planning accuracy on the utility side, and it builds stronger, more collaborative customer relationships. It's about being partners, not just order takers.
Proactive infrastructure, standardized solutions, integrated planning, financial innovation, specialized resources, and market engagement. Okay. So let's bring this home. What does this all mean for you, the listener, depending on your role, whether you're in utility management, transmission, distribution, or planning?
Right, let's break it down. For utility management, the big picture is that data center interconnection isn't just an engineering problem, it's a competitive advantage for your utility and your region.
Opportunity, not just challenge.
Exactly. That infrastructure banking concept. It needs regulatory support, yes, but it demonstrably delivers customer value. And remember, specialized teams and processes consistently deliver better, faster results. Invest in that specialization.
Okay, for transmission engineers.
Your secret weapon is pre-positioned transmission capacity. It tackles the biggest timeline bottleneck head-on. Don't underestimate standardized substation designs. They can probably handle 80% of data center needs, simplifying your life. And grid-enhancing technologies. They are invaluable interim solutions while the big steel is going up.
Good point. For distribution engineers.
Voltage level selection. That is probably the single most critical design decision you'll make early on for these projects. Get it right from the start. Avoid those parallel feeder headaches. Modular designs are your friend for handling uncertain load growth, both timing and magnitude. And never forget, power quality requirements are absolutely non-negotiable. Design for them from day one. Don't try to band-aid it later.
Critical advice. And finally, for the system planners.
Scenario-based planning. It handles the inherent uncertainty of data center development far better than traditional load forecasting. Those integrated transmission and distribution studies, they are key to reducing overall project timelines. And engaging early, talking directly with developers, it dramatically improves your planning accuracy and builds those crucial relationships. It's a win-win.
That's a great summary for each role. This has been really comprehensive, a deep dive into what's working, what's not, and how utilities can actually succeed in this space.
It really shows the challenges are huge, but, the opportunities for innovation and improvement are just as significant. It's a dynamic field right now.
It certainly is. And looking ahead next week on the PXRD newsletter, and right back here for our next deep dive, we're going even deeper into some specific technical areas reshaping the grid.
Oh, yeah.
Monday, we kick off with FERC Order 1920. We'll explore how those new 20-year planning horizons are revolutionizing transmission design. We'll talk about the 7 key benefits that will change how you evaluate projects, how you can engineer for 2045 today, and why grid-enhancing technologies are basically your new essential planning toolkit.
Sounds fascinating. That order is a big deal.
Huge. We'll even explore how FERC Order 1920 creates some really exciting new engineering opportunities in the field.
It really is an incredibly exciting and challenging time to be an engineer in this industry. The pace of change is just something else.
It truly is. And as we close out this week's series focused on data centers, maybe here's a final thought for you to consider. This data center boom, it represents both the biggest infrastructure challenge and probably the biggest opportunity our industry has faced in decades.
That's a powerful way to put it.
The utilities that master these solutions, the ones that really embrace this challenge as an opportunity, they're going to be the ones defining the grid of the future.
Absolutely. And we really do believe the engineering community learns best from real-world experience. So we encourage you to share your own utility successes, share the lessons learned, even the tough ones. Let's keep this conversation going.
Couldn't agree more. If you'd like to leave feedback or if you have any questions about today's deep dive, please feel free to reach out to us. You can email me at alex.reed.power.podcast@gmail.com.
And you can reach me at emma.quinn.power.podcast@gmail.com. We'd love to hear from you.